So good morning and welcome back to Optical Interconnects, and we are starting another very exciting day of Hot Interconnects with this keynote from Fuad Doany from IBM T. Watson. So Fuad took his degree in physical chemistry at the University of Pennsylvania, then he went to Caltech for a few years, and after that he moved to T. Watson, and he did a trailblazing career in optical networks and technologies. So get ready for this tsunami of technical information. I mean, I went through the slides and they are really impressive. And perhaps outside the formal technical introduction, I can say something about the real contribution of this team and of Fuad, in optical interconnects. So when we design exa-scale, and if you had to do an analysis of the keywords that we say most of the time, so cost is probably one of the most frequent keywords, right? So we know that in order to get to that level of performance, we also need some performance boundaries, but also some cost boundaries. And in order to do that, it's fundamental that we break the cost, performance, and power barriers that are in the optical network. We perceive that probably one of the biggest hurdles to reach, the next generation of supercomputers and also data center machines. So I'll give, without further ado, I will give Fuad the chance to talk about this great technology, and I'm sure you guys will really love this type of presentation.
Okay.
Thank you, Fuad.
Thank you for the introduction, Patricia. Can you hear me? Microphone on? Well?
Is this working? Yes, it is.
Sorry for the technical delay. If it was done with optics, we wouldn't have no problems here. So I'd like to thank you for the introduction, and good morning, ladies and gentlemen. I'd like to tell you, I'm very pleased to tell you about our work on power-efficient, high-bandwidth optical interconnects for HPC systems. I feel a little bit out of place here at this meeting because I work on technology, and more specifically optical interconnect technology. But we all know that optical interconnects are playing a major role in these large server systems. Today, systems are being designed that heavily rely on optics. Basically, they cannot operate without the optics. So I'd like to give you a presentation to give you an understanding of optical technology today, where we have been in the server world, the state of the art today, and more importantly, where we think we're headed in the next few years. I'll start by thanking a lot of colleagues at IBM Research in Watson, as well as in the Zurich lab and the Tokyo lab, and some colleagues at Server Group, some collaborations with some external companies, as well as partial DARPA funding for the IBM Terabit program. And the all-important disclaimer that the opinions I'll be expressing here are solely of myself and don't represent anyone else. So we all know optics have been displacing copper for over 3 decades now. Initially in long-haul telecom applications, and then in local network datacom applications, and more recently at the system level in computer comm applications. But computer comm spans a whole range of interconnect distances, as you're all aware at this meeting, from system level, rack to rack, intra-rack, module to module on a board, chip to chip in a module, or even within a chip. And the bandwidth distance advantage of optics compared to copper is leading to widespread deployment at shorter and shorter distances. But as distances go down, the number of links goes way up, so we have pressure on power, efficiency, and density of these modules. So the outline of my talk is shown here. A very brief 2-slide introduction of what I think are important parameters for optical links. I'll give you a brief history of optics in HPC and what are the demands for the future systems. And then most of the talk is about our work at IBM Research to optimizing power and efficiency of these links, including some very recent results on pushing the speed and power efficiency, and some concluding remarks at the end. So a very brief fiber optic intro. Today there's 2 camps of fiber optics. There's the telecom and the datacom, computer comm world. Telecom deals with tens to thousands of kilometer distances. It's very expensive to install fiber at these distances. So they rely heavily on wavelength division multiplexing, where they have data coming over many wavelengths over a single fiber. Performance is a primary concern. Component cost is secondary. These relative bulky, power-consuming components, but reliability and long life is critical. Whereas datacom, computer-com links, they're 100 meters or shorter. Cost here is the biggest factor. And transceivers are commodities. We use multimode fibers and lasers. These essentially have a 50 micron optical core as opposed to a 9 micron in telecom. This gives you greatly relaxed alignment tolerances and assembly tolerances. And reliability is less an issue here because these are pluggable modules, but as we talk about systems with hundreds of thousands and millions of links, then reliability may come back into it. And the reach is relatively short and typically use parallel optical transceivers, arrays of lasers, arrays of photodetectors, and arrays of fibers. So what I mean by optical links is the middle portion of this chart right here. We've taken input electrical signals from your system, CPU or switch, and the green box is the transmitter optoelectronic module. It has this laser driver circuit, a 3.5 semiconductor laser, and a laser bias supply. We modulate the light, couple it into a fiber or waveguide, detect it at the other end in a receiver module, which has a photodiode and a transimpedance amplifier, a series of limiting amplifiers, and a 50 ohm driver to drive it back into your system. This is what the part I'll be talking about, the green part in the middle here. And by far the most common 3.5 laser in this case for datacom is the vertical cavity surface emitting laser. This is a gallium arsenide substrate where we grow epitaxial layers to form a high reflectivity mirror. The active region is a 1 micron layer in the middle, and the additional layers on top form a partial reflector, and the laser lasers in the vertical direction. Here's an SCM photograph of the laser. You can see the aperture is about 5 to 10 microns. So these are very low power devices, low threshold that can be modulated to high speed directly. The cost is much cheaper than the edge emitting lasers used in telecom applications. It can make high density 2D arrays. The point about the cost is that they can be fabricated at a wafer scale and tested at a wafer scale. So we can make 2D arrays of these, and they don't require much temperature control. They operate over a 40-degree range, as opposed to telecom, again, where we need 1 degree temperature control using thermoelectric coolers. VCSEL by far dominate this industry today, shipping millions per month, and they typically can cost on the order of $1. So let's talk, I'm going to go quickly through this section. This is the evolution of optics in HPC systems. This is the obligatory chart here that everybody knows that the trends are going at an exponential growth in the high-performance computing world. The number one system is growing at 10x factor every 3.5 to 4 years. Just 4 years ago, we hit a petaflop. This year, a 10 petaflop system. And just a couple of months ago, IBM introduced the Blue Gene Q system at the Lawrence Livermore, which reached 16 petaflops. And the projection is continuing at this rate. We expect to be at an exaflop before 2020. And this trend is maintained for the top 500 machines shown here. And we're all aware that this performance is all by parallelism. It's not the processor speed. It's an aggregation of a massive number of multi-core processors. And there's challenging interconnect bandwidth, which is the subject of this meeting, across all system levels. And just to point out that optics are now penetrating the system at shorter and shorter distances. So in 2002, the number one system, supercomputer system, is the NEC Earth simulator, had no optics at all. Bulky electrical cables routed underneath the floor. In 2005, IBM had the ASCII Purple system at Lawrence Livermore, 100 teraflops, many racks, as you can see, and use a combination of electrical and optical links. You can see the bulky electrical links for the shorter rack-to-rack links, and the orange optical links for the more than 20-meter optical links. This system used commercial so-called SNAP-12 optical modules, roughly 40 by 20 millimeters in dimensions. They have an electrical interface at the bottom, and a fiber interface to couple to a 12-channel fiber connector on the side. They're mounted at the edge of the card, and this system had 3,000 links, about operating at 2.5 gigabits per second. In 2008, there were two systems that achieved the petaflop milestone, the IBM Roadrunner system and the Cray Jaguar. These systems both have a lot more optics in them. You can see that the Jaguar system had about 3,000 active optical cables. The IBM system had over 5,000 active optical cables, about 55 miles of optics. These were 4+4 transceivers. The active optical cable was a lower cost solution than the discrete modules and optical fibers. So all rack-to-rack links were optical. The system had about 40,000 optical links. And if you look at the distribution of the links in the system, it's 98% of them are less than 50 meters. This is the area that we're working on, 50 to 100 meters maximum reach for optics. So, and this system operated at 5 gigabits per second. Where we are today, the state of the art is 10 gigabits per second modules. So I think the next level of evolution would be to move the optics close to the logic rather than the edge of the card. As you can see at the edge of the card, there's a couple limitations. One is there's a bandwidth limitation by the number of pins from your first level package to the system board. And two, at 10 gigabits, you need a very expensive circuit board and a lot of power and equalization to drive to the edge of the card for these optical modules. So if we move the optics closer, we can avoid the power distortion cost of this electrical link. And if we move the module onto the first level package, we can break through the pin barrier also. This is the packaging that was demonstrated last year in the IBM Power 775 system. We can see here a photograph of the hub or switch chip on the MCM. There's sites on the MCM for 56 optical modules. The optical modules were co-developed with Avago. They're micropod modules. They're 12-channel, 10-gig modules. But more importantly, the density is greatly improved. This is roughly an 8 by 8 millimeter module as opposed to the 40 by 20 we used in the previous generation. These are packaged, 56 of them, onto a module, and you can see the fibers, 28 fibers going to the left, 28 fiber ribbons going to the right. Now these are tightly integrated in the PERCS drawer, the Power 775 drawer, shown here. It has 8 32-way SMP nodes, and you can see around the orange area, the right of that drawer is all optical modules. There's 8 of these modules. So there's 8 times 56 optical transceivers on this drawer, and they're routed to the edge of the card. The bottom picture shows that the back of the card is mostly taken up by these optical connectors. The left, right, and middle, as you can see, these are a massive array of 48-channel fiber connectors. Within the rack, you can put up to 12 of these drawers. Here's an example of the optics for the outer links shown. This is the rack-to-rack links. Not shown in this picture are the additional optics that would go in the center, would be for drawer-to-drawer within the rack. This is essentially the optical backplane links. Looking more carefully, you can see how dense these 48-channel optical modules are packed. There's a fully populated rack will have up to 60,000 fibers, about 5,000 optical modules. Today, just recently, Fabrizio and his team introduced the Blue Gene Q. It's the #1 computer achieving 16 petaflops. And you can see here the orange optical links between the racks. And there's all rack-to-rack links are optical, and some of the inter-rack links are also optical. It has 330,000 VCSELs and fibers. And if you look at the drawer, it's a 32 compute node drawer, and the optics are in the back of the drawer and routed to the front. There's 36 12-channel modules. These are the same modules used in the Power 775 system, and they're aggregated into 40-channel fiber connectors. So this is where we are today. Where we're going to be in the near future? Well, I took a reconstructed table here from the DOE RFI for exa-scale, and just point out a couple of things on it. One is that this system is expected to be delivered by 2019 or 2020, in the near future. Power consumption of 20 megawatts, and the node-to-node interconnect bandwidth is roughly 400 gigabytes per second. So let's just assume you'll do all 400 gigabytes per second optically. And if we assume a lightly interconnected system of about 0.1 bytes per flop. So just using these numbers, we get that every picojoule in optical link power consumes about 0.8 megawatts of system power. Every 10 cents per gigabit per second cost results in $80 million in the system cost. So how much power can we devote to optics, to interconnects in general? Today's numbers, the best numbers of these transceivers is about 25 picojoules per bit. That amount would equal the network power, would be the total system power of 20 megawatts. So clearly we need to go much lower in power. Is 5 picojoules per bit enough? That may be enough as an intermediate step. It's probably not good enough for exa-scale systems. So as you can see, this computer comm is driving the development and large-scale deployment of optical interconnects. So rack-to-rack links are extensively deployed today using conventional optical modules mounted at the edge of the card. The intra-rack systems, we saw the first examples using dense, parallel fiber-coupled modules mounted close to the CPU. The next step in a few years, we believe, would be a module-to-module optical link on board using integrated transceivers and optical PCB technology. And eventually, 10 years down the road or more, we can see a 3D chip stack with a photonic layer, and that would certainly require silicon photonics. So the two areas I'll be talking about are these two areas here. These are short-reach optical links optimized for power, cost, and density. And we know for exa-scale, we're going to need picojoules per bit at cents per gigabit per second. So now I'd like to tell you about our work at IBM Research to try to optimize the power and efficiency of these links, as well as develop a very large number of channels to achieve terabit per second kind of optical module. So one is packaging integration. I've already talked to you about optics co-packaging, bringing the optics close to the CPU. We already have seen examples of that. The next step may be optical printed circuit boards. These are printed circuit boards that have optical polymer waveguide layers that can provide a high bandwidth optical link between modules on the board. We're also working on chip scale integration. We no longer want to use these bulky optical modules. We'd like to use Optochips. And Optochips are essentially flip chip components of optoelectronic arrays and drivers forming a compact chip-like package that can be integrated into your carrier. We're also doing a lot of work on optical link improvements. We're working on advanced CMOS and other techniques, and I'll show you some results how we're achieving record densities, record efficiencies, and high speeds here. And silicon photonics, I'm not going to talk too much about that. I'll mention it just in the slide as a possible new technology. It has the potential for low power, high density. It's a single mode fiber solution which has longer reach, certainly. And the primary advantage, we think, is WDM and density. So optical PCBs. The idea of optical PCBs, we want to go from this picture that we have today of the spaghetti of fibers and large modules to an integrated solution that has polymer waveguides integrated in the card and optical components, or Optochips, attached to your multi-chip modules. So the vision is that we have an optical MCM. Optics are co-packaged with the logic. It has several advantages. We can use low-cost pick-and-place packaging to assemble these modules onto the card. The polymer waveguides will provide passive routing and splitting function. And we bring optics close to the processor for maximum performance. And we can enable the use of low-cost FR4 because the high-speed signals are all transmitted through the optical waveguides. And we've demonstrated examples of this. Here's one shown down below. We have a link through polymer waveguides between two modules. You're looking at some infrared-sensitive camera that can see the scattered light. The idea is shown below in the cartoon. It's an optical module that has an integrated transceiver. The PCB has a waveguide layer along with a turning mirror and lens array. So the module with the optical transceiver looks like a surface mount electrical chip carrier. And as you solder this to the card, you can simultaneously provide electrical and optical interconnects. And the optical high-speed connection between the two modules is supplied through the optical waveguides. So we've demonstrated this complete technology, both the PCB with polymer waveguides, chip-scale transceivers or Optochips, and integrating these Optochips on the MCM. I'd like to just give you some highlights of the optical PCBs. Here's an example of the work. This was done at the IBM Zurich lab. We use polymer waveguides on a low-cost FR4 substrate. We do lithographic patterning, and we've demonstrated on the pictures on the right here shows the waveguides that are 48 channels, 35 micron cores at 62.5 micron pitch, very dense. The cores on the inset shows the cores 35 micron high index polymer embedded in a low index polymer. We can do this directly on the FR4 as in the top picture, or we can do it on a flex waveguide that can be attached to the FR4 at a later time. You can see that this is a link of 48 channels between two module sites. The top half of the picture shows 36 channels going from the two sites, and 12 channels are routed to the edge of the card. And we can enable waveguide to fiber coupling at the edge of the card to go to a different card, for example. And we demonstrated waveguide to fiber connectors shown here, 1x12 as well as 4x12. We demonstrated waveguide flexes that can provide shuffle function. And the final step is we demonstrated the full optical PCB by having turning mirrors and a lens array added to the assembly. We have low loss waveguides, about 0.05 dB per centimeter at 850 nanometers. The plot below shows a scan of the loss across 48 channels of an optical waveguide. And you can see relatively low loss, 3 to 4 dB across the entire length. For optical coupling, we use a two-lens optical system. There's one lens integrated into the transceiver and one lens integrated into the polymer waveguide with a turning mirror. The advantage of a two-lens system is that we have collimated light between the two systems. So with collimated light, if you offset the two relative to each other, you still get good focusing of the light into the waveguide. And the graph on the right shows that we have, this is the coupling efficiency versus offset. And we can see that for the transmitter, we have 35 micron tolerances, and for the plus minus, and for the receiver, more than that. So these are large enough tolerances that we can use pick-and-place packaging tooling. And the final step to complete the assembly is that we've taken the optical modules shown below. The bottom view shows that it has an integrated lens in the center. We align lens to lens to the optical PCB, and we can, as we solder the two, we get, again, the electrical and optical connection simultaneously. And here's some examples of what a full assembled module on the PCB. All right, this is the PCB part. The transceiver part we've been working on for the last few years at a path to achieve a terabit module. And we have 3 generations of Optochips. They all use exclusive flip chip packaging for maximum performance and density. In 2008, we had a 985 Optochip that achieved 240 gigabits per second each direction, 2010 up to 360, and this year we achieved a terabit data transfer out of a single module. They can be designed for waveguide or fiber coupling. As a matter of fact, the first two were used for waveguide coupling, and the recent one for fiber coupling. So let's talk about the first generation. It's a 985 transceiver. 985 presented the simplest packaging. We have a CMOS chip. It's only 3 by 5 millimeter. It has 16 laser driver circuits, 16 receiver circuits. We flip chip the 4 by 4 array of lasers and photodiodes onto it directly. And the advantage of 985 is that the gallium arsenide substrate of the VCSELs and photodiodes is transparent. So rather than fabricating the VCSELs and photodiodes to emit at the top, we can fabricate to emit at the bottom, the back of the chip. And this way we can integrate lenses directly in the gallium arsenide to collimate the light. So this is simplest packaging. We built these modules. We built a full link, shown here. There's 16 channels going from left to right, and 16 channels going from right to left through the polymer waveguides. Operates very clean eye diagrams at 10 gigabits per second. So total of 32 channels. We achieved up to 10 gigabits per second through the polymer waveguides. The limitation here is that the polymer waveguide at 985 is quite lossy, so that was the maximum data we could achieve through the polymer waveguides. But the modules themselves actually did significantly better. You can see on the left is the transmitter module, 16 eye diagrams at 20 gigabits per second, very clean, good performance at 20 gig. And for the receiver, offered up to 15 gigabits per second. And the receiver represents a full transmitter to receiver link. At 15 gigabits per second, this module has an aggregate data rate of 240 gigabits per second in each direction, and a power consumption of about 9 picojoules per bit. All right. The next generation was a migration to 850 nanometers. The datacom industry today is at 850 nanometers. There are many suppliers, it's lower cost, and the multimode fiber is optimized for 850 transmission. Another advantage for us is that the polymer waveguides have much better loss numbers for 850 than 985. And Typically, we can achieve 0.03, 0.04 dB per centimeter loss, which means that a 1 meter link can have 3 to 4 dB, which is manageable in your link budget, whereas a 985, it doesn't seem feasible to achieve a 1 meter link. But we wanted, at 850, the gallium arsenide is not transparent, and these have to be top emitting devices. So, but we wanted to retain the same packaging approach of a module that looks like a surface mount electrical carrier. So we developed here for the 850 the silicon carrier Optochip. It basically has a silicon carrier as a platform to integrate the components. It's a laser driver, laser array, photodiode array, and receiver chip on a silicon carrier. The silicon carrier then has optical vias, or holes, essentially, for to emit light out the back, and we can integrate a lens. And the rest of the module looks very similar to what we had before, this organic carrier with the integrated Optochip. So what we changed is the Optochip itself, not the packaging concept. And for this project, we used 24-channel lasers and photodiodes. So this is what the silicon carrier looks like. It's 6.4 by 10.4 millimeters. It has 150 micron thick silicon. 3 layers of wiring to interconnect the OEs to the ICs, the optoelectronic arrays to the ICs. In the center where the OEs are attached, we have optical vias, holes in the silicon. We can then flip chip attach all 4 components, the laser, the photodiode, the receiver, and the transmitter IC. And we get a module Optochip that looks something like this. The light comes out the bottom through optical vias. This is a poor picture, but you can see here the optical vias in the center. And the electrical I/O comes out through silicon electrical vias to the package. We packaged this on an organic carrier, shown here. It's a 35 millimeter organic high-density, high-speed carrier with a vision that this would be your future multi-chip module. You can co-package the logic, memory, whatever you need. And you can get high-speed interconnect between the modules on the carrier. But off-carrier, the high speed is carried out through the Optochip. And if you look at the bottom of the chip over here, of the module, there's bond pads to attach this to the card. And at the center, we add a lens array for the optical output to the optical PCB. This module shows very good performance here. We demonstrate 24 channels at the transmitter, operating at 20 gigabits per second. Again, uniform clean eye diagrams across all 24. And the receiver operated up to 15 gigabits per second. Typically, the receiver has more bandwidth limitations. These were tested with optical fiber links and achieving a 360 gigabits per second bidirectional data rate. It has uniform performance. This is a little more technical information, but here this is a measurement of the receiver sensitivity. If you plot the bit error ratio as a function of received power, you can see, for example, at 10 gigabits per second, all 24 channels fall in a very tight range with a sensitivity of about minus 14 dBm. The laser typically puts out between 0 and 3 dBm, so we have a very large margin for the optical link. But as we go to higher data rates, the eye degrades somewhat and we get less sensitivity in the link. And this is basically a limitation of partially the VCSEL performance, but more in the receiver bandwidth. We mounted a couple of these modules on the optical PCB, and this time using a flex waveguide. And you can see here, using, again, an infrared camera, you can see 6 channels going from left to right, all the way up to 24 channels. And at the maximum data rate we can of 15 gigabits per second, we were able to get 15 channels from left to right, and 15 channels from right to left to operate error-free, a bit error rate of less than 10 to the minus 12. This is a record optical bus on PCB, 225 gigabits per second in each direction, and a power consumption of about 9.7 picojoules per bit. The final generation that we just introduced this year is what we call the Holy Optochip. It is essentially a much more integrated solution. Rather than having a silicon carrier with optical vias and 4 components, we condense this to a single chip CMOS that has the laser driver and receiver circuits. We integrated the optical vias in the CMOS, and then we can flip chip attach the VCSELs and photodiodes. So this is a much more dense integration, simplified packaging, more similar to our 985 picture. For this project, we actually built a fiber-coupled module. This is the cartoon of what it looks like. The Optochip is in the center. It's based on CMOS. We then flip chip attach it to an organic carrier. We also demonstrated a pin grid array pluggable connector to demonstrate that these modules can also be swapped in the field. We have a two-lens optical coupling system and a standard 4x12 fiber, multimode fiber here. So our goal here was to get 24 channels, transmit and receive at 20 gigabits per second for a total of 1 terabit transfer rate. It's a single chip CMOS with a wafer level post process to create the optical vias. And we have the optical system we showed before. Here's an example at the bottom left that shows a module under test where we have a 48 fiber connector being aligned to the Optochip down below for optical coupling. And the fully packaged module looks something like this. We added a heat spreader and a tight bend radius 4x12 fiber connector with a total height of less than 10 millimeters here. So a little more detail. It's a 90 nanometer CMOS, bulk CMOS process standard, relatively old technology now. And we do a wafer scale process to etch deep silicon rye process to etch the optical vias in the center. And then we can flip chip attach these custom 2x12 VCSELs and photodiodes to the center. And we get the Optochip shown here. It's about 5.2 by 5.8 millimeters. And if you look at the bottom to the optical vias, you can certainly identify the individual lasers and photodiodes. They're arranged on a 250 by 250 pitch to match exactly a 4x12 fiber connector. So we can couple this directly to a 4x12 fiber. Again, we use an organic package that's roughly 17 millimeters. The size of the package is completely determined by the BGA pitch when you attach this to the system board. In this case, 0.8 millimeter pitch. And we demonstrate additional functionality by having a pluggable connector. It has a socket half that you solder to the circuit, to the test card, and a pin half that you solder to the module. And here's the fully assembled module. Again, you can see the Optochip in the center with optical vias exposed, and the VCSEL and photodiode are at the bottom surface of this. To test this module, we have a test card shown here that has the connector, the Optochip on the module, and we need 96 high-speed electrical connectors to access the 48 differential inputs and outputs of the module. So using this test setup, we looked at the eye diagrams of all the channels. Here's a typical transmitter channel, operates from 15 gigabits up to 22 gigabits per second. So at 20 gigabits per second, we get relatively clean eye diagrams. Same for the receiver. At 22, we get to see some degradation, but certainly is open at 20 gigabits per second. We are able to demonstrate on one chip all 24 transmitters working, and on the receiver, again, all 24 links working here at 20 gigabits per second. And I have a plot here of the bit error ratio as a function of the power, and you can see that all 24 channels operate error-free, although not without margin. We're pushing the CMOS technology to the limit here to operate at 20 gigabits per second. So this is 480 gigabits in each direction for a total of 1 terabit, and the power consumption was about 7.3 picojoules per bit. Another goal of ours was to demonstrate 5 picojoules per bit, which this did not demonstrate. But one of the reasons it did not demonstrate it is because of the packaging. In the previous case, we have a connector at the bottom of the module. We have a couple centimeters of transmission line on the card, and so this packaging can degrade the high-speed performance. So to look at the performance of the intrinsic performance of the Optochip, we had a second organic carrier where the electrical signals are kept on the surface and can be probed with an electrical probe. So this is the intrinsic performance of the Optochip, not including the packaging. And here we were able to get, there's an optical fiber input and electrical input here, and we achieved 18 links operating a bit error rate less than 10 to the minus 12 at a total power consumption of 98 milliwatts, which corresponds to 4.9 picojoules per bit. This is full power end-to-end, including the lasers and all the CMOS circuitry in here. I'd like to keep these numbers in mind. I'll bring them back in a couple of slides for comparison. The Optochip is a complete transceiver in about 30 square millimeters. It can deliver the terabit data rate. It can potentially be packaged directly into an MCM at this kind of density. The current implementation is limited by the BGA pitch of the test card. Comparing it to a standard module today, the best module you need 6 micropod modules that consume about 600 square millimeters of area to achieve 1 terabit compared to this Optochip. So this is the densest demonstration of about 32 gigabits per second per square millimeter. All right, so this is our work on parallel transceivers and optical PCBs to demonstrate terabit per second data transfer. Let's talk very briefly about silicon photonics. Silicon photonics can take up more than an hour by itself, and I think there'll be talks more about silicon photonics. It has potential for low power, high density. It uses half micron waveguides in silicon. Again, it has longer reach. It's suitable for WDM. But silicon is a very poor light source, so these transceivers typically use an external laser input. And the silicon photonics technology provides the modulation. And there's two types of modulation typically used, is a Mach-Zehnder interferometer and a ring resonator. A Mach-Zehnder interferometer basically takes the input beam, splits it into two waveguides, and when you recombine it, you can either, if you introduce a phase delay in one of the arms relative to the other one, you can modulate the output light. Because silicon is a poor electro-optic material, using CMOS voltages, you need on the order of 1 millimeter path length to achieve this sufficient modulation. So that's the Mach-Zehnder modulator. The ring resonator is a very compact device. It's roughly 10 micron radius ring. It's a ring that's placed adjacent to a waveguide, and light can couple to the ring for a very narrow resonance. Basically, you have a notch in your transmission through the waveguide if you're at the resonance of the ring. And this resonance is so narrow that just a slight change in the index can shift this resonance and modulate the light very efficiently. So it could be a very low power device. I'm not going to talk too much about it. I just want to say that these can potentially be low power devices and very compact, but we have to consider the full link power: the modulator, the circuit, and the laser. So let's go back and look at the power numbers I just showed you for our 4.9 picojoule link. The laser driver circuit consumed 26 milliwatts, the laser itself 10 milliwatts, and here are the numbers for the receiver. This is the laser power. For a comparable silicon photonics-based transceiver, let's look at the projected numbers. Mach-Zehnder and ring resonator. First of all, they both have the advantage on the receiver side. They have an integrated germanium photodetector, which has very low capacitance, so you can use a higher gain TIA, and thus you need much less amplification in your limiting amplifier chain. So it can have a 30% advantage in power here. On the transmit side, the high-speed laser driver is about the same. The difference comes in the device. The Mach-Zehnder is a long distributed modulator that requires roughly the same power. The ring resonator can have negligible power essentially, but only for this part. You still have the laser driver part, which is again about a 30% savings. And we still have not included the laser and the temperature tuning required to keep the ring in resonance. So compared to VCSELs, I think Mach-Zehnder resonator interferometers, modulators are very comparable in power, and ring resonators can be lower power. So we think, but you have to add the laser also. The primary advantage we think is WDM and density and not necessarily power. But these must be implemented in a cost-effective way. Now, there have been recent examples of about a picojoule per bit transmitters and receivers using this technology, but again, the laser was not included here. All right, that's all I want to say about silicon photonics. Other than that, once you include WDM, you can manage a different problem here, which might be a fiber management problem. As we get to 1 million fiber links in the system, you're going to have a harder time managing fibers. This is the Power 775 system. It looks all right, but you look below the floor, this is what the cable management looks like in some systems. And how do you manage 10 times more fiber in the future? Well, then you need some sort of WDM, more bandwidth per fiber. VCSELs also have the potential of demonstrating this. We can do coarse WDM with VCSELs, or you can do multi-core fiber. Coarse WDM was demonstrated a few years ago by Adjunct Labs in their MAUI project, where they took 4 wavelengths, 4 1x12 arrays of lasers, shown here, and they built a micro-optical module that can mux the light here, shown here, where we can, using interference filters and optics, you can transmit one wavelength and reflect the other ones, and combine the 4 wavelengths into a single fiber. This worked. It's kind of lossy. It has a 4 to 5 dB TX loss, 2 to 3 dB RX loss, but they did demonstrate this. They built a whole transceiver with using silicon germanium, achieved 10 gigabits per second per channel at about 7 picojoules per bit. So it's been demonstrated. The challenge here is the cost and packaging. We're working on an alternative approach where we can put multi-core. This is not the multi-core you're used to. This is number of cores in a fiber. Typically, in the fiber about 125 micron diameter, we have a single 50 micron core. Well, why not put more cores? Here's an example of a fiber that has 26 micron cores. There's 7 of them. And the challenge for us here is how to couple 7 lasers, or actually specifically 6 lasers, we can't couple the middle one, into a single fiber. And the WDM challenge is the manufacturing of the mux and demux and cost issues, basically. So we obtained some of this multi-core fiber, and we used some of our existing Terabus hardware to demonstrate a link. We see here we have our silicon carrier I showed you before with the receiver transmitter and the 2x12 arrays of VCSELs and photodiodes. But instead of 2x12 arrays of VCSELs and photodiodes, we fabricated 24 lasers and photodiodes clustered in groups of 6. So this has 4 clusters of 6 lasers and photodiodes. The bond pads are the same location as our old array, but the lasers and photodiodes are in clusters of 6. We built this on the silicon carrier. If you look at the bottom here, you can see the 48 optical vias of the silicon carrier, but only 4 transmitters are populated and 4 receivers are populated. You look through these optical vias, you can see the individual hexagonally packed lasers and photodiodes here. We coupled them to a fiber with 7 cores, and we can align the 6 cores on the outside to couple to the lasers and photodiodes. And we demonstrated here 120 gigabits per second over 100 meters using a single strand of fiber. So these 2 technologies have potential, can lead to more bandwidth per fiber. There are cost challenges today, but we're working on advancing this technology. Running out of time, so let's talk to you about our work on single channel transceiver test sites to determine the technology limits and what future directions we need to go. So rather than building these 48 channel devices which consume a lot of area, we built single channel sites, and we can populate a whole variety of variants on the wafer. So here's an example of a CMOS transmitter and receiver that achieved 25 gigabits per second, the first for CMOS. We have a single channel laser driver, wire bonded to a VCSEL. We couple to a fiber and go to a photodiode that's wire bonded to a receiver IC. And we showed performance up to 25 gigabits per second for both. Another advantage of this setup is we can basically keep turning down the bias voltages for all the components and find out what the minimum power you need for error-free operation for this link. And that's shown here. This is the power efficiency as a function of data rate. We see initially it goes down because the CMOS and laser have a minimum power requirement. And so the efficiency improves. But at some point, it starts to increase again, because to get error-free operation, you have to add more power into the system. So what we achieved in here basically is 2.6 picojoules per bit, again, end-to-end, wall plug efficiency for at 15 gigabits per second, and about 3 picojoules per bit at 17.5 gigabits per second. We also had some more experimental variants on these sites. We have an experimental inverter-based receiver that we use instead of the previous receiver. And here we achieved, here are the eye diagrams at 15 and 20 gigabits per second. Here we achieved 1.37 picojoules per bit at 15 gigabits per second. Again, here's the power efficiency versus data rate, and you can see there's a minimum, 1.3.7 at 15, and still 1.42 at 17.5 gigabits per second. This is a record low power for any optical link in any technology, and certainly this is the power consumption of the order required for exa-scale. So another knob we have to play with is the transmitter and receiver equalization. This is a technique that's extensively used in high-speed electrical links. So the idea here is that we can provide adjustable pre-emphasis on the electrical signal to the laser. So this is a typical laser driver. Before we get to the output stage, we tap off part of the signal, delay it, and combine it with the output. and we can get essentially pre-emphasized electrical signals that go to the laser. And here, what it would look like, you can see the pre-emphasized signals in the eye diagrams, but it provides a much more open eye at the higher data rates at 20 gigabits per second. And we've used this for CMOS. We've also used this for SiGe for very high data rates up to 40 gigabits per second. So here's an implementation of this technology in a link, the transmitter feed-forward pre-emphasis. We use this pre-distortion to compensate for the combined VCSEL speed, the TIA and limiting amplifier bandwidths here. And we optimize the full link performance. Without this FFE turned on, you can see that it works very well at 15. It's completely closed at 20. And the eye looks open at 17.5. But if you actually do a more quantitative measurements of the timing margin, basically if you look at the horizontal eye opening as a fraction of, and quantify it as a fraction of the bit period, at 15 gig, about 50% of the bit period is open, is error-free. At 17.5 gig, the eye actually never reaches error-free operation. And then you apply the equalization, and you can see the eyes open up at all data rates, and quantitatively here at 15 and 17.5 is a wide open eye. In addition, although we added some power to the link, it actually is much more efficient. If you plot the power efficiency versus data rate, we can go to higher data rates and a much more efficient operation. And we achieve data rates that we couldn't achieve without this. So we did transmitter equalization. What about receiver equalization? So we applied transmitter equalization to go from to improve the laser performance as you detect it in the receiver. We can also apply receiver equalization, which is typically used to drive through packages. In this case, demonstration, we drove through 10 inches of circuit board. So without equalization, at 20 gig, the eye of the VCSEL looks fine. The receiver is completely closed, and you don't even recognize the eye after 10 inches of circuit board. So then we apply equalization. It's not to improve the TX output or the RX output, but it's used to optimize the full link, the eye at the final destination. And you can get very good performance here at 20 gig through 10 inches of circuit board. So we use the equalization to optimize the full link, not to beautify the TX or RX eyes. And this ends up being not costing you a lot of power. If you look at the breakdown of the power in this link, the transmitter has about 83 milliwatts, the receiver about 124, but only 5.4 and 3.9 of that is the equalization, this is pre-emphasis. This is a simple single tap pre-emphasis circuit. Of the total power, it's less than 5% consumed for this. This is just a summary of where we have gone in just in a few years, about 10x improvement in efficiency. We started at about 7.5 picojoules minimum. We had improved circuits that achieved about 2.5. The novel experimental circuits that went down below 2. And in the near future, we'll be publishing this paper that basically achieved less than 2 all the way up to 25 gigabits per second. So VCSELs have demonstrated capability of getting close to the picojoule per bit number here. Just one slide left on data. This is the silicon germanium technology. Silicon germanium is used for the higher speed performance, and typically that's what's in transceivers today. It's higher power, but also higher speed. We want to use this to explore the limits of VCSEL speeds. So here's an example of a link we built with silicon germanium technology using 20 gig VCSELs. And you can see it operates at 25 gigabits per second, but it's not very well at higher data rates. Even 35, it's not error-free without equalization. We add the equalization. We pre-distort the laser, but the full link is wide open, and all the way up to about 43 gigabits per second. So we have still room in VCSELs to go up to higher data rates. This is with 20 gig VCSEL designs. Perhaps with future VCSELs, we can go even further in speed. I'll skip this part. So just to summarize, how to get to these power density numbers that we're looking for exa-scale. We've shown dense hybrid integration can achieve very high performance. Optics close to CPU, optics co-packaging, shown here, and these integrated Optochips. We believe another step in a few years might be optical PCBs, where you have an optically enabled MCM, where the Optochip is co-packaged with your other chips, and the high-speed signals are routed through polymer waveguides. We've worked and continue to work on advanced circuits, and we believe in CMOS scaling. This is what's all done with 90 nanometer CMOS. We expect to get better performance in speed and power as we go to newer generations of CMOS. We can use SiGe for ultimate speed, and there'll be continued VCSEL improvements to help us along with these speeds. My last slide, comments and outlook. The number one message here is that VCSEL transceivers are evolving to meet exa-scale needs. We've demonstrated record powers and speeds and densities here. VCSELs are not dead yet. I think we have a ways to go. And I think we'll see coexistence of VCSELs and silicon photonics. There's no one-size-fits-all solution today. For example, datacom and computercom are totally different technologies today. The critical challenge for silicon photonics is packaging today. They've demonstrated the various components. You got to be able to integrate them and package them in a low-cost way. We're working on new approaches that will be required for exa-scale. We're working with shrinking margins to meet the aggressive power numbers. We're going to use every technique we can, the equalization, advanced circuits, optical PCBs, and all these other advanced technologies. And future exa-scale, computercom, cost, density, performance requirements, we need a holistic approach to design and manufacture these optical interconnects. We can't design them separately from the system. We need to work closely between the system manufacturer and the optical component manufacturer. So these may seem like daunting challenges, but I think they open many opportunities for innovation. Thank you very much.